Hey guys, if you're here because you wanted to see the derivation for the equations that I used in my other example video for Matlab ODE 45, where I had this physical system and I got these two-dimensional equations and all that fun stuff. Or maybe you got here by accident and meant to see a Matlab video, in which case I'm sorry. You can navigate to that video instead. But if you want to see the derivation, you can stick along for the ride. You'll notice that I'm not going to be writing things out. Instead, I have stuff planned out in a Word document. And that's because writing this out would take a lot of time. It would make the video really long and probably, even more boring. So instead, I've already typed all the steps out and I'll guide you guys through those. I do still have the drawing up, and I've added the X, Y, and Z coordinates along with the I, J, and K directions. And I've also specified this height H, which we'll be using for potential energy purposes. I did not write L here, but know that there is this radial length L, right, for this pendulum. And again, keep in mind, mass 1 can move left and right, and mass 2 is attached to mass 1 through this kind of massless pendulum bar guy thing. We're interested in knowing what x is over time and also what theta is over time. And we'll be getting our equations of motion using Lagrange's equations. You'll often find that when you're dealing with multi-degree of freedom systems, or MDOF systems, that using Lagrange's equations is much easier than using force moment balance methods. But, if you were to derive this out yourself, you could do whatever you wanted. Don't let the equations scare you off. I will say that if you haven't had like some Calc 3 experience or, some vibrations experience especially, that maybe you don't want to watch this video, but if you still want to watch it, that's okay too. Here's the equations we'll be working with. T stands for the kinetic energy of the system. D stands for the Rayleigh dissipation function for the system, which for our simple system will really only involve the damper. And V stands for the potential energy of the system. Capital Q is some generalized force. Lowercase q is some generalized coordinate. It could be x, it could be theta. And this capital Q is the generalized force for the coordinate that you pick, that corresponds to the coordinate that you pick. To tackle this problem, the easiest way to tackle it would be to get the individual terms first, get T, get D, get V, get capital Q, and then from there we can just plug and chug and do all the math. So let's do that, starting off with T, or starting off with the kinetic energy of the system. So, if you're familiar with basic physics, the kinetic energy of any mass is just 1/2 mv squared. Notice that this is the magnitude of the velocity squared, not, some vector squared, although I don't know how you would square a vector, I guess. Anyway, we're looking at the magnitude of the vector, the velocity vector, squared. The velocity of mass 1 is very simple. Mass 1 can only move left or right, so its velocity would be x dot, the time derivative of x. And it's moving along the positive I hat direction based on this convention, so the velocity for mass 1 is just x dot times I hat. Now, looking at this mass 2 here, its velocity is a bit more complicated. And we can think of it by thinking of two individual scenarios. If we were to hold this bar still, so that theta is not changing, right, and we were to allow mass 1 to move back and forth, because mass 2 is rigidly attached to mass 1, mass 2 would share the same velocity as mass 1. This means that mass 2 would also have a velocity of x dot times I hat. But that's only one part of the story. If we were to instead hold mass 1 still and allow mass 2 to swing back and forth, we would see that we have some angular velocity going on here. And that angular velocity would be theta dot, the time derivative of the angle theta. If we want to know the linear velocity at some instant in time, we could just use that, or rather get that, using r omega, or in this case L, which would be our radius, times theta dot, which would be our angular velocity. And you want this velocity in our I and j components. For that, we can just use cosine theta and sine theta to break it out into the I and j components. Very simple. And for anyone who might get confused, the velocity vector for mass 2 is having an angle with the horizontal, not the vertical, right? This angle over here, theta, is with the vertical. However, the velocity will be perpendicular to this pendulum, right? This bar here. So the velocity is going this way, and the angle that it sees would be with the horizontal. And because of that, the cosine theta would give us the I term, and the sine theta would give us the J term. Hopefully that didn't sound too confusing. I know I didn't explicitly draw it because that would make the drawing look more cluttered. But that's how we get the velocity for mass 2. Then you want to get the magnitudes of these velocities, and we can get that by summing the square of the individual I, J, and K components. There's only an I component for mass 1, so its magnitude is just x dot squared for velocity 1. For velocity 2, it only has I and J components, no K component, so we square those individual components and add those up. I didn't want to stop there. I wanted to see if there was any more simplification that I could do with this system, so I expanded this guy out, and I realized that I could group these two terms together by factoring out an L squared theta dot squared. I did this here, and then I realized, you know what, cosine squared of theta plus sine squared of theta is just 1. So this is what I have here in the end, this expression for the kinetic energy of the system. Next, we can do the potential energy for the system. And for that, we see that there are two possible sources of potential energy. There's the spring, and there's also mass 2, because we realize that mass 2 can move up or down, giving it or taking away from it potential energy. We can set the reference point to the bottom, where the bar is vertically straight down and mass 2 is as low as it will ever be. If we set that as the reference frame, then whenever mass 2 swings up, it will have moved some distance h. To get this distance h, we can subtract the original length when it's straight down, which would be L, from the length it will be at vertically if it swings some angle theta. And this vertical length would be L cosine theta. If we subtract those two, we get L minus L cosine theta, and I jumped around, sorry about that, which is this guy here, right? So here's the potential energy, 1/2 kx squared plus m2gh. I transform, or rather substitute n for h, L minus L cosine theta, because you want things in terms of x and theta. And then I factor out this L here and get this final expression for the potential energy in the system. So that's taken care of. Then we have the Rayleigh dissipation function. Again, that's really simple. There's only one source of damping here. We're ignoring drag forces here, so we only see a 1/2 c times x dot squared for the Rayleigh dissipation function. Finally, we want to get the generalized forces of the system. If we're looking at the theta coordinate in mass 2, we realize that there aren't any forces or moments being applied over here, so both of these terms would go to 0, and we do indeed see that for Q2. For Q1, as we're looking at mass 1, there are no moments being applied on this guy either, but there is a force being applied to it. So this term is important to us. The force vector is in the I direction, so the force vector is just f of t times I hat. And we also need the location vector and the generalized coordinate. The general coordinate is obviously x, and the location vector is x times I hat. Really easy. We plug all that stuff in, we do dot products and partial derivatives and all that fun stuff, and we realize that Q1 is just f of t, which would make sense because there's only one force acting on mass 1. So now we have all the t's and d's and v's and q's, so we can start looking at Lagrange's equations for the individual variables. Starting with x, you see that I replaced all the q's with x's, and q is now Q1. I'm going to go ahead and plug in these terms, this dt dx dot, dt dx, dd dx dot, and dv dx. Plugging in those derivatives, I end up with this expression here. Notice that dt dx is 0, as we see here. I simplify this by expanding or factoring out this 2 to get rid of the 1/2. I then take the time derivative. For the first two terms, this is very easy. X dot just becomes x double dot. For this last term here, both this theta dot term and this cosine theta term are, functions of time. And so I'm going to have a product rule. And then with this product rule, the second term will have a chain rule. right? Lots and lots of fun. After doing all of that, I get my final expression, my final simplified expression for the first equation, and here it is. Next, we move on to the theta variable. With the theta variable, all the q's have now been replaced with thetas, and we now see q2 for q. Again, plugging in the derivatives, we have this expression here. Notice that d theta dot is 0 because d had no dependence on theta dot. Again, I factor out the 2 to get rid of the 1/2. And then I take a time derivative, which again involves a product rule that also involves a chain rule for the second term. After doing simplification, I get this expression here. And so now we have two nonlinear equations of motion. And they're clearly nonlinear because we see these squaring terms and these trigonometric terms also. That's what we want to get rid of. But in order to linearize these equations, we need some point to linearize these equations about. Alright? So we want to look for the equilibrium positions. To find the equilibrium positions, you set all time-dependent forces to 0, and you also set all velocities and accelerations to 0. So this has an acceleration, that goes away, this goes away, this goes away, this goes away, this stays. It's a position term. This goes away, this goes away, this stays. Again, we have no velocities here, no accelerations. This is okay staying where it is. Simplifying the equation that way, we end up with these two equations to find our equilibrium positions. And we see that there are two possible equilibrium positions actually. Two solutions, 0, 0 for x naught and theta naught, or 0, pi. Now we choose one position specifically because we're assuming that this mass does not start up all the way, up here. Alright? We're assuming that it starts down here. And if that's the case, then the equilibrium position would have theta naught being 0, not pi. So we choose x naught theta naught equals 0, 0. And after that, we can finally linearize the equations about the equilibrium position. And we're going to assume small vibrations or small oscillations while we're doing this. This is extremely important for a few reasons. First of all, first let's go ahead and talk about the linear stuff, the linearizing about the equilibrium positions, okay? Doing that, because theta is 0 at its equilibrium position, and we're linearizing it about that position, right? As long as theta stays small, then all of our cosine of thetas just become 1s, and all of our sine thetas just become thetas. And when we're doing this, we have to be sure that our theta is in radians, not degrees, because of this assumption. So as you'll see here, I've kept these terms bold to show where I made changes here. Where these guys had cosine thetas, they now have nothing there, equivalent to multiplying it by 1. And where these guys had sine thetas, they now have just thetas. Now, another important thing is this assumption about small vibrations or small oscillations. And what this means is we're not assuming that these guys are moving wildly out of place. This mass 2 is not swinging over these huge angles, right? We're assuming that it's just, swinging ever so slightly. We just see these small vibrations in theta. We're seeing these small vibrations in x. Okay? And with that being the case, that allows us to make some simple assumptions. Again, if we make that assumption, if theta stays small, then our whole idea of linearizing about this equilibrium position is safe, because theta will never be really large. It'll stay around the 0 area, so the cosines of theta are 1, and the sines of theta are thetas. But more than that, if we have these small vibrations, then terms that have anything like theta squared or theta times theta dot, things like that, those terms we can also cancel out. Because think about it. A fraction, if it's multiplied by another fraction, will only get smaller, assuming that it's a proper fraction, right, where the numerator is smaller than the denominator. Fractions multiplied by fractions only continue to get smaller. So if theta is small, and theta dot is also small, then theta dot squared times theta is going to be extremely insignificant compared to the rest of these terms. So that's why you see this slash through it here. We can just cancel that out. And after that linearization and after that simplification, we end up with these equations, these final linearized equations of motion. So there's the derivation that you guys wanted if you stayed along for the ride. Now, one thing that I was curious about, and maybe some of you are curious about too, is what would happen if we worked with these nonlinear equations of motion, right? Could we get this in state space format and then get Matlab to go ahead and, check out some nice numerical results? And the answer to that is yes. Now, I'm not going to derive out the state space form for these nonlinear equations. And why? Because it takes time and effort. If you look over here in this Matlab function that I've created here, just look at this guy at the end, all right? This is the state space format. Obviously, S2 and S4 are easy. They just be there. But these terms here, with all these sines and cosines and secants and everything, I mean, in this last term here, I had to, continue it to the next line, all right? This is not pretty. It's not. If you want to derive it out by hand, you can. If you want to see the final result, I mean, here's the final result here, where S1 is x, S2 is x dot, S3 is theta, and S4 is theta double dot, right? And then you can see this total result here. If you derive it out by hand, you may get a different expression depending on how you simplify out your terms. But when you look at the numerical result, you should get the same numerical result that I'll get. But here's the result here. I don't want to derive it out, too much time, and even showing it is just a drag and boring. So let's run this and see what our results are for linear versus nonlinear. We run this and look at that, all right? Now you might be wondering, where in the world is the linear solution, okay? When you plot things in Matlab and your axes, as long as your axes are okay and nothing weird is going on, if you don't see the first function that you plotted, that's because the first function has been completely overlaid by the second function. Now what does that mean in this case? That means that the nonlinear solution has completely overlaid the linear solution. Exactly. Which means, significantly speaking, the nonlinear solution is pretty much the exact same as the linear solution. And that might seem crazy, but I mean, it makes sense. We made assumptions. We made assumptions that we wanted to be, safe assumptions. We assumed that theta was really small, right? We have these small vibrations, and so that allows, when we're linearizing about our EQ positions, that allows for simplifications of cosine theta and sine theta and crossing out certain terms that are not significant. And we see that, indeed, the two solutions look very similar. Now, obviously, they're not completely exactly the same because the nonlinear equations involve some other terms that, weren't included in the linear equations. I mean, just look at this. This linear setup is clearly simpler than this nonlinear setup. And indeed, we can zoom in further and further to these solutions. If I zoom into this guy, and then zoom into it some more, and then zoom into it some more, you can begin to see the linear and nonlinear solutions, right? There is some differences, or there are some differences between these guys, right? And same for this guy. If I were to zoom in for the theta results, zoom in some, and then zoom in some more, and then zoom in some more, and zoom in some more. It's harder to see with this guy. And zoom in some more, and zoom in some more, and some more. Ah, there we go. We can see clear differences now, but the timing of these differences, the significance of these differences is extremely small. All right? And if we move out of both of these guys and see the bigger picture, we see that, yeah, these solutions are pretty much the same. They're not the exact same, obviously, but again, they're pretty much the same. So the lesson to be learned here is that linearizations can be very useful. They can be used to simplify a problem and allow you to get results that are accurate and that very well represent your system. Of course, you have to make sure that your simulations are, or your approximations are viable. And you can usually only find that out from simulation unless you have certain experience that you're going off of. But if you verify your approximations, then yes, doing a linear or approximation of a linearized system is very much valid. and you'll see that it's worth it. I mean, look at all this work that we have to do. We did all this work, or I did, setting up this nonlinear system, and this setup for the linear system is so much easier, and in the end, the results were not significantly different. And that means we could have also done this in the matrix format that I'll show in the other video, where there's a much faster way to handle these problems. So yeah, just let that be, kept in your mind. I'm sure you've already heard this from some other course that you've taken, where approximations are not always bad. The results from approximations can give you significantly accurate results compared to the, quote-unquote exact model that you're working with. That's all that I have. I'm sorry that I only did this using the function method. I really didn't want to write out things for the mfile method and the function handle method also. So here's the code. You'll also see me using global variables, and sometimes it's frowned upon, but sometimes it makes it easier to organize your code. So please don't hate for that. But here is the function method, and you'll notice that I had to make two separate functions at the end of this function for the linear and nonlinear systems. And there's probably a way to make this neater too by, continuing to the different line, to the next line earlier than I did there. But that's everything. I hope you enjoyed this video and were able to learn or be reminded of important concepts from it. Let me know how helpful it was in the comments below. And again, have fun in your Matlab ventures. Thanks for watching.